So, looking at then externally reflected component, one way is to simply find the sky factor. As I said, you can find it from the table. That is again given as L by D, H by D, and I just forgot to mention sky component tables. There are two sets of table. One is for horizontal surfaces, another for vertical surface. For example, if it is a blackboard in a school, board in a school, so how much daylight you receive, so that is for the vertical one. Same principle is applied, because the points you can take onto the vertical surface, and same principle is applied. So, there is one table for vertical ones, one table for the horizontal. So, and then there is a third table for sky factor, there is a table for sky factor as well. Now, sky factor again you can find out in another manner. How? See, you have found out the basically we found out from basic principles, but supposing I know the sky component for that area and divide by its average brightness, then also I will get the sky factor. Am I right? Because you see the sky component actually I found out for a given, for a small area if I consider, and average brightness, let us say, which is L OBS, or I mean L of the sky, sorry, L sky. So, I have found out sky component for same integral etcetera etcetera. Average, if I take in a small area I consider, this area is small, then I can say that for that area I can take the average sky brightness, divide the sky component by average sky brightness, that will be the sky factor again. Because if I assume that the brightness is constant, which is average value, so from sky component also I can find out from the sky component also I can find out the sky factor by dividing it by average brightness for that zone, average brightness for that zone. So, that also can be done. So, sky factor can be obtained in that manner. So, basically sky component divided by L sky we are saying is nothing but sky factor, nothing but is also sky factor. So, this is also sky factor, but if sky component is usually is given as E sky divided by E SC, illumination due to SC divided by E 0. So, I multiply again by E 0. Let me repeat, what is sky component? It was actually E sky, ESC divided by E 0. What is ESC? ESC divided by average obstruction of the sky, L OBS will give me sky factor, this will give me sky factor. So, sky factor can be obtained in terms of so this sky factor can be obtained in terms of this. Sky factor is sky component multiplied by E 0, that is nothing but illumination due to that portion of the sky, and if I divide by the average brightness of the sky, then I get sky factor. Average brightness of the sky factor is independent of the brightness. Sky factor we said is just integration of sin 2 theta by 2 d theta d phi over theta 1 to theta 2 the obstruction area. We are assuming that obstruction area is having uniform brightness. So, sky they are also having uniform brightness, which I am calling as L sky, So, let me just rewrite this again. So, let me explain, and E sky component is equals to divided by E 0 is equals to sky component SC. So, ESC is nothing but E 0 into SC, all right, ESC. Now, ESC divided by L sky on both sides, L sky, that should give me sky factor, that should give me sky factor. So, sky factor is nothing but E 0 into SC divided by L sky. So, that is what we are saying, sky component E 0 divided by L sky. So, that is what we are saying, sky factor is this. Now, sky factor therefore, you can find directly from the table or also from the sky SC value, which is again from another set of table. So, you can find out, but E0 is known to you, which is 8000 lux, and L sky is known. But supposing this is given as a ratio, this is given as a ratio, then you can, it is given as a ratio, you can multiply simply sky component by this to get the sky factor. Okay. So, these are given in tabular form. First of all, as I said that brightness of the obstruction, for that purpose 3 types of sky have been, 3 types of obstruction has been classified. One is a sunlit, one is sunlit, directly direct sunlight is reaching onto the obstruction, that is the building next. Non-sunlit without any obstruction. So, it could be sunlit means this is your building, obstruction I am talking of, and it receives the sunlight, it receives the direct sunlight. So, that is the sunlit. There can be another one which is not sunlit. So, here it would be something like this is not there, this portion is not there, but the sunlight comes from there, let us say, and your point is somewhere there. So, this is non sunlit, but there is no obstruction to that building itself. Now, supposing this building itself has got an obstruction, may be obstructed, the sun is coming from this side and your building is somewhere there and this is obstructed. So, it is shadow, I mean it is under, it is not receiving direct sunlight, but obstructed, and this will also, this will actually contribute to the sky component to this building itself, this, it will also contribute to the sky component, like externally reflected component to this building itself. So, there are 3 possibilities: sunlit, non-sunlit without obstruction, and non-sunlit with obstruction, right. So, it is classified in 3 class, and for each of them actually this value is given. What is given? R obstruction value is given, reflectivity of the obstruction is given, reflectivity of the obstruction is given. So, reflectivity of the obstruction is given, or what is given is actually in a tabular form, E obstruction divided by E 0, E obstruction by E 0, this is given in tabular form, and R obstruction values are given, and one can obtain these values again from table and multiplied by sky factor to get ERC, multiplied by sky factor to get ERC. Let me see if I can solve a problem that would make it life easier, looking at the table, but is actually looking at the table, because E of the obstruction, illumination of the obstruction, that of course one can calculate out by E 0, but these are given on a gross manner depending on angle. Similarly, E 0 by L sky is given by 1 by inverse brightness factor, 1 by BF. It is called inverse brightness factor for the obstruction. As I said, the sky factor can be obtained from E 0, it can be obtained as ESC into E 0 by L sky, and E 0 by L sky is given, E 0 by L sky is given as 1 by bright, it is called inverse brightness factor, 1 by BF. Now, this 1 by BF value is tabulated for various angles of obstruction, because it involves L sky. So, this will change with the angle, this will change with the angle. So, this is 1 by BF values are given in a table for various angle of elevation or average angle of elevation of the obstruction, right. So, ratio of design sky mean, okay, this is given, reciprocal of this is called brightness factor. So, this is what is given. Let me see if I have, something like this, something like this, something like this. For example, this is your obstruction. So, mean angle of obstruction is this. This is the total, this is the overall angle of obstruction, mean angle of obstruction is this. So, for this one in table 1 by BF is given. So, this will vary from 5 degree to 85 degree. 90 degree means it is fully blocking, everything is blocking, 90 degree is very unlikely to have something like this. If this is your working plane, nearly 90 degree means somewhere here, but so it is given for 5 degree to 85 degree 1 by BF, and what is 1 by BF? 1 by BF is nothing but E 0 by L sky. So, this value multiplied by sky component from the table will give you sky factor. Sky factor you can obtain, use this sky factor together with these values which are given in table, because E obvious by E 0 is given in the table, and R obvious is given for various conditions like sunlit, non sunlit, etc., etc. So, from this table one can find out right? From the table one can find out and then use them for finding out the externally reflected component, right? But the principle I have told you. Principle is what? You assume the brightness of the obstruction is constant, and you know the area which will contribute to the EERC, area of the obstruction, which will contribute. And you can then integrate it corresponding theta 1 to theta 2, theta, etc., etc. You can actually integrate it accordingly. So that is how it is. But then this has been done using, the table have been formed for various L by D and H by D using same principle. But today if you write a program yourself, you can actually do it that way. So that's the principle. And in order to, in order to have the brightness of the obstruction, again it's given in tabular form, whether it's sunlit, non-sunlit with obstruction, or non-sunlit with no obstruction. So the three cases, and also I believe the colors or something is given with respect to that, something of that kind is given, types of surfaces. So these values are given in a gross manner and one can calculate these. So that's the principle of calculating ERC. I'll try to solve one problem sometime. I think I'll try to solve one problem sometime. Now for IRC it is done in a slightly different manner. That is, what is IRC? Internally reflected component. So what is done is, if this is your window, this is your window, you divide it into two parts. Principle wise, you divide it into two parts. At the mid height, this is your window actually, this is a window. So mid height you divide into two parts. Now light through this window will come from the bottom, because there will be some ground reflection. The sun rays are received onto the ground as well, and there will be ground reflection coming in, and there will be coming direct light from the diffused sky radiation will come here. Diffused sky radiation will, or from obstruction it might come somewhere there. Some light will come here. So what is done is, it is assumed that the flux coming here, bottom half of the window, comes from the ground. Flux coming from top half of the window, sorry, it's other way around. Comes top half of the window, comes from the sky or obstruction, and they are first reflected from the floor and these walls below the bottom portion. So what is assumed is that the light that comes from top half of the window is first reflected from floor and up to the mid height of the window, walls up to the mid height of the window. It's assumed that it is actually reflected from all the walls up to the mid height of the window, but not this wall, because it is coming through that. So if you are considering one window, that wall you leave out. First reflection occurs from here, because you are interested in FR. And remember principle of integrating sphere, it was FR divided by 1 minus R, right, 1 minus R, and divided by area of the internal area of the room. So this principle we are trying to apply, and therefore first we assume, everything got cancelled, doesn't matter, so I'll redraw it, no problem. So I said mid height, so this so I divide the flux into two parts, FCW and FW. What are CW and FW? FCW, or let me write it, I think it was somewhere here. Flux is F, and the principle I apply is first reflected flux divided by this, the integrating spheres principle. So what we do is we divide into two parts, FCW and FFW, right. So that's CW is the one which goes to the ceiling, that means it comes from the ground. FCW is the one which goes to the ceiling, so it comes from the mid height is this, so the one that is coming from the ground, that goes to the ceiling, first reflection. Then reflectivity of this top half of the room I consider, leaving this wall, reflectivity of the top half above the this mid height of the window. So, reflectivity of all the walls, ceiling, etc., I calculate up to this wall, do not consider this. So, up to this I calculate out reflectivity, average reflectivity. How is this average reflectivity? Area weighted. Same way we did it for absorption coefficient of sound. So, it will be actually R1 A1 or Ri Ai sigma this, right, divided by sigma Ai, sigma Ai. So, that is weighted average I am calculating, but then this I meant for all the surfaces other than the wall containing the window, right, and above the mid portion of the window, mid height of the window, right. So, it goes up and everything. So, this is similarly as far as this comes, this flux comes from the top, goes to the floor and reflected, first reflection goes to. So, this RFW is the reflection coefficient of all the surfaces below the mid height of the window, that is your floor plus half the half up to the mid height of the wall areas up to the mid height, leaving the particular wall on which the window is there. Now, if you have window in many walls, you will do for individual one and then sum it up, because they are all scalar quantities and you can sum it up. So, this total is summed up, this total is summed up, this total is summed up divided by, when you calculate this R, this R all the surfaces you got to take into account. Why? Because second reflection onwards everything will take part in reflecting. First reflection, only first reflection comes either from the bottom half, that is including floor, or from the ceiling top half, but infinite reflection it will reflect from the same window as well. If it is open, then obviously you take the reflectivity equals to 0. Reflectivity is, if it is an open window, you take reflectivity is equals to 0. If it is a glass, then actually you take reflectivity of the glass. Actually glass transmits about 0.85. Is assumed the glass transmits about 0.85. So, that is multiplied in the formula, and 0.15 its reflectivity. So, you take the glass reflectivity if the glass window is not open but closed. If it is open, then you take it 0, but take this R all surfaces, all surfaces, all surfaces, including those, including that of the wall having window itself, having the window. So, you take this for all, you take this for all, while this you take leaving the wall on which the window is, and only this is for ceiling and this is for floor, and this flux are now to be assumed. So, this what we are saying is coming to the ceiling, the flux, this should be flux coming to the floor. So, for whole room, R is for whole room, that is what I am saying. FCW is multiplied by W by 2, window area is into the illumination at the window surface, illumination at the window surface, that will be the flux, illumination of the window surface multiplied by W by 2. So, illumination at the top half of the window surface, ceiling, sorry, ceiling it goes to the bottom half, sorry, no, top half of the window surface, FCW is here. So, the flux that goes up actually. So, in any case that is the illumination, and this is that goes to the floor. So, illumination of the window surface must be known. Now, this has been simplified further, or rather W by 2 area of the window into A divided by AR. Now, this is written in terms of some constant, this is written in terms of some constant C2, and this is written in terms of some constant C1, right. Now, these values are given in the, these values are given. C2 is going to the ceiling, so it comes from the ground, right. So, assuming the ground reflectance to be about 18%, it will depend upon vegetation type, the location type. For example, if it is subtropical, it could be 10%. In a tropical hot dry desert area could be about 18% or 20%. So, Indian code takes it to be 20%. So, this is all in percentage. So, this is taken as C2 is taken as 18% reflectance, right, 18% reflectance, and C1 depends upon the, if you have an obstruction. If you do not have an obstruction, that value would be 78. Again everything is in percentage divided by E0. E0 is also been taken into account. No, 17 is 78. So, this value is 78 for 68 for 5 degree angle of obstruction. So, if angle of obstruction is 5 degree, for example, in this diagram if you had this angle of obstruction is 5 degree, right. Here it is showing the full obstruction. Actually, if this angle is 5 degree, then this value is taken as 68, because 5 degree means 85 degree, most of it is for 10 for 85 degree or fully obstructed. So, if the obstruction is full, because then the light comes from external obstruction only. So, IRC is contributed by flux coming from the external obstruction. So, if it is 85 degree or full, then this value is much less. If the sky is open, then you get 78 fully open, 68 for 5 degree angle of obstruction, little bit is obstructing, rest all is free. So, this is again given in table. So, C1 value is given, C1 value is nothing, but the one comes to the floor, right. So, this divided by E0 has been already done. So, elimination not is yeah, this is already done actually. ERC multiplied this constant divided by E0. So, this C1 C2 divided by already E0 is taken into account, and this is how you can calculate out. So, what all that you have to do is first calculate out the RFW, RCW and R. A stands for total internal area including the window and everything, internal surface area, and C1 and C2 you have to, and this is the window area. C1 and C2 you have to determine. C1 is C2 you take 18 straight away, because IRC will be in terms of percentage. 0.85 is taken if it is glasses are closed. So, assuming that transparency of the glass is 0.85, and R is calculated in this manner as explained here, area of the ceiling into R of the ceiling, area of the floor into R of the floor, area of the wall into R of the wall divided by AC, everything, all this divided by sum of all this, that is what is R. As far as RW is RFW is concerned, FW is concerned, this part will be there, this will not be there, and here it will be half of those area minus the area of the wall also. So, RFW, RCW will calculate accordingly, and this is the formula for internally reflected component. This is the formula for internally reflected component. This is the formula for internally reflected component, right. So, that is how you calculate out. Now, this is this principle, only thing which will again matter here is these values, that will depend upon sky type, but I believe that these numbers have been adopted from international research only. These values that is given, this because you find in many of those illumination book daylight, early daylight books, these values are similar. This is taken, many other places taken as 10% for subtropical climate, because reflectivity of relatively greener surface, what you see in cold climate, or that would be relatively less for sunlight whenever the sunlight is available. Here it is taken 18 for, they took it 18, or some cases is taken as 20%, so 20. So, this is how we can calculate out IRC as well, right. Okay. So, this is how you analyze point by point, but some qualitative ideas. So, what we have seen is we can calculate out SC, we can calculate out ERC, and we can calculate out IRC, right. So, these calculations we can do, but then there is some kind of gross understanding. There is something called daylight factor contours, sky component contours, not daylight factor, because IRC will be constant throughout the room, including vertical or horizontal surface, because it is a diffused one coming from all points. So, IRC will be constant throughout, right. ERC will go from point to point again, and sky component will go from point to point. So, we talk in terms of something called sky component contours, because that will depend upon your fenestration area. Now, you see the window area is coming everywhere and window location is coming everywhere. So, if you want to design, it is designed based on window location and area of the window, height, L by D, H by D, etc., etc. So, this is a typical 1% sky component contour. This is your window, 2.1 meter is shown here, and this portion is called spread. This is called spread of the daylight factor contour, and this is called penetration. This is called penetration. Penetration. And your common sense would tell you, if you increase the height of the window, the penetration for any percent, you can take 1% sky component or 2% sky component contour, penetration will increase. 1%, let us say, is minimum daylight sky component, minimum sky component you want to ensure. So, you want to find out how much is. So, penetration will increase as height of the window increases. If width of the window increases, then spread will increase. So, here it is 2.9 meter, 4.4 meter depending upon the window, and depending upon the window. So, under design condition or any condition that you can find out. So, these are called spread and penetration. Spread increases as you width of the window increases, height increases, then penetration will increase. But beyond 5-6 meter you do not find the spread and penetration so much. For example, this for 1% contour, sky component contour, this for 2%, this for 3%, this for 4%. So, the contours equal sky component contour. So, they like a bulb, they spread. So, light 1% sky component means E0 multiplied by 1% means 0.01, you will get around 8,000 into 0.01 is 80 lakhs, am I right? So, 1% of 8,000 is 80 lakhs. So, 80 lakhs, this is the 80 lakhs line having 80 lakhs. So, if you have measured them or calculated them, making them small areas, and then you can make a contour plot. Similarly, if you have two windows, they would be something like this, right. So, 6%, 9%, 1% contour might look somewhere there, because they will merge. It might come something like this, or sometimes they will merge also, 1% contour, some of them merge. So, spacing of the window is important. If the spacing is less, then they will merge and overall they will give better one. And if it is in one side, then you get something like this, 1% contour is something like this. So, this is 7%, 3%, 2%, and that is how it is. So, if you have more of such diagrams are given, for example, if you have window here and here, then you might get something like this sort of contour, you might end up getting this sort of contour. So, if one window here, one window there. So, first initial one will be like this, but beyond that you will have something like this, then you might get something of this kind. So, the daylight penetration spread increases in this manner. What we have seen is in analysis, there are some design guidelines available, but they are fairly empirical, based on this kind of calculations only. So, point by point analysis is possible. You want to find out qualitatively larger the area, more will be the daylight penetration or daylight inclusion. Penetration you want to increase the height. Spread you want to increase the width. Then you can do the calculations point by point. If you want to do, you can do this calculation and find out how is the pattern of daylight there. So, this is how one can do some sort of typical design. Some design charts are also given in SP 41, determining possibly window size, but they are based on similar kind of principles, not really much more, not further details. So, that is what it is. Now, in tropical climate, usually light color surfaces of we use light color surfaces for other building. Why? We want as much as less absorption as low alpha value. We want alpha value lower for thermal reasons. Now, you have high whitewash surface which will have high reflectivity. So, they are sometimes source of glare. So, hot dry climate, light color surfaces of obstruction, and they might be sources of glare actually. So, it is better to increase the IRC, and IRC increase means reflectivity of the surfaces, inner surfaces should be as high as possible, because if you see it was related to IRC 1 minus R is IRC is proportional to 1 minus R, right, and then RCW and RFW. So, if you reduce the R, this value increases, of course, this value increases, right, but first reflected component anyway this 7, but overall R having more reflection having, sorry, if you increase the R, what will happen, this value will small, 1 minus R, you increase the R, this value will be small, IRC will increase. IRC increases with increase of R, IRC increases with increase of R, right, 1 minus R. So, as R increases, 1 minus R will reduce, and 1 by 1 minus R will increase. So, IRC will increase if I increase the R value, more reflected light. So, it is important to have a maintenance of the even internal surfaces, so that it does not accumulate dust. Maintenance factor, we call something called maintenance factor, which varies from 1 to 0.7. So, more frequently you maintain the inner surfaces and make them more reflective, better. So, IRC increases. Besides that, IRC also you can increase by putting the fenestration somewhat above the near the ceiling. What is the point is, then you will reduce the glare. Glare, this I mean this kind of concepts one can apply, but then this is not very easy to do. For example, you can have this reflected from outside or reflected from the ground. Some of them can result in glare. This can result in glare, reflected from outside obstruction. Sometimes in desert area this can be very bright, so they can cause glare. So, exclude view of bright ground and sunlit louver, and then what you can do is increase this by putting your, if possible, some daylight and allowing fenestration area at the top, because then directly you will not see them, but this may not be feasible all the time. So, usually light color surfaces, IRC you try to maximize, and exclude view of bright ground and sunlit louver, because that can result in glare. So, maximize the IRC as far as possible. That would be the typical idea of tropical climate. Anyway, north surfaces are better if you are in northern hemisphere. Southern faces are better, because that will not bring in direct sunlight. But then you should not be seeing sunlit obstruction also. That is what is being said. Okay, so that actually, so Indian design methodology I have just covered. I have just covered Indian design methodology. So we can attend some of your questions, and then next class we will look into something more, right.